All right, welcome everyone to class again. And today I will be teaching musical instruments. Yeah, so basically we'll be looking at the perspective of the physics for musical instruments. Please pay rapt attention, make sure you're taking notes, and pay attention to the concerned formulas and calculations. Let's have a deep dive into this. All right, I'll be sharing my board at this time. Yeah, and here we go, musical instrument. Before I dive so deeply into this concept, musical instruments, before I dive deep into this concept, I would love to talk about the characteristics of sound wave. Characteristics of sound wave. Let's talk about that. Characteristics of sound waves. Let's just use this as the building block to what we're about to discuss. Characteristics of sound wave. I would say number one of that is sound can be musical or noisy in nature. Sound can be musical or noisy in nature. So take note of that. Very important point. Then we also say sound waves can be produced. Sound waves can be produced. Sound waves can be produced by vibrating a material medium. And that material medium can be solid, liquid, or gas. When vibration occurs, sound waves can be produced. Or we can say by a vibrating object. And then this is where we have things like the guitar, strings, and air column. In physics, most of the time we talk about the air column and strings. Air column in pipes. Air column in pipes. Take note of that. So between the frequency of, let's say, 20 and 2000. So let's just keep it at this. Let's just stop at this. Now let's go to music. Let's talk about music and noise. Music and noise. What is music? Or let's define a musical note. A musical note is a combination of sounds of definite, please take note of this, definite and regular frequency. So musical note is a combination of sounds of definite and regular frequency, and it is characterized by pitch. It is characterized by, you're just going to list them out: pitch, quality, loudness, or intensity. So keep that in mind. Let's now quickly talk about noise. Noise is a combination of sounds of irregular frequencies. Are you following me? Yes. I expect that you should be taking notes, and this particular point would help you with some of your multiple choice exams and maybe even theoretical aspect. It is also regarded as an unwanted sound. It is a combination of sounds of irregular frequencies. Let me just continue that statement. And can also be regarded as an unwanted sound. Unwanted sound. So keep that in mind. Let's quickly, I mentioned some characteristics of musical notes there. Pitch, quality, loudness, intensity. Let's quickly dive into that. What is pitch? Let me call it important concept. Important concept. What is pitch? Number one, pitch. What is pitch? Pitch has to do with the position of a sound in a musical scale. So just put that one in your memory. Position of sound in a musical scale. And the pitch actually depends. It depends on the frequency. Depends on the frequency. So it's whenever you hear the pitch, it differentiates the sounds of encouragement from the sound of annoyance. You understand? It differentiates an annoying sound from a soothing. A soothing. Soothing means like cool, calm, soothing sound. So soothing is spelled Soothiing. In case you wanted to spell it wrong. In case you didn't see exactly what I wrote here. But that's just the point about pitch. We don't want to waste time there. Let's go to quality. Quality. Oh, sorry about that. Quality. 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 Another name for quality is tone. It is also called tone or timbre. Timbre. And it refers to the nature of sounds on the basis of their sources. Please focus, rapt attention. Nature of sounds on the basis of their sources. E.g., the sound coming from, a pure tone. Let me just write it down. Sound from different musical instruments. So, for example, the sound coming from a guitar is never going to be the same as the sound coming from a saxophone. Never. Different musical instruments. Are you following me? Yes. The sounds with single or pure tone. Pure tone. Yeah. So, and others. Let me just stop giving examples at this junction. Let's say ETC. Okay. Sounds with single or pure tone. Yeah. Let's go to the next thing. The next thing is let's talk about loudness. Loudness. Yeah. Loudness and intensity. Loudness and intensity. Loudness and intensity. Intensity in itself has to do with the time rate. The time rate. Whenever you hear time rate, it's more like something over time, something per time. Time rate of the flow of energy flow of energy, unit area, perpendicular to the direction of the wave. Keep that in mind. So if we are going to write a short formula for that, intensity looks like I equal to change in E all over T dot change in A. Change in T dot change in A. So basically, this guy is, let me just write out the parameters, what they mean. Change in E, this is like the energy. Then when you say energy, this is the other one, change in A, that's like the area. And then change in T. It's more like the time. So please keep that in mind. Just keep this formula important. I'm going to put it in red, so you pay close attention to it. Let me cover it better. Okay, here we go. Formula for intensity. No, this one is of capital importance because sometimes it surfaces in OBJs. I mean, your multiple choice questions, and then they can just ship it in somewhere in the theory sometimes. So pay close attention to that. How about we use the concept of power? If we use the concept of power being, oh, let me switch back to black ink. If we use the concept of power, we know generally in physics that power is equal to energy divided by time. I mean, the work rate, the time rate of energy. So if we are to substitute that into the formula for intensity, we would have, we'll now be having, let me just use an arrow. It makes our intensity formula to be written as, look at this part where you have change in E over change in T. We can replace that with, what? With power. Are you with me? Yes. So we have P over, what are we left with under? Change in area. Yes. So please keep that in mind. Let me put that formula also in red. Please rapt attention, focus, and just go with the flow. You will need some of these things jotted down so that you can rehearse them and use them in preps for your exam. So the next thing I'll be talking about is that this intensity we are even discussing at this time, it varies with amplitude. Okay, and I'm going to write how it varies with amplitude for you. It varies with amplitude, it varies with frequency as well. So the intensity is directly proportional to the square, directly proportional to the square of the amplitude. And so we can write that as I, this is the direct proportional or proportionality symbol. I directly proportional to a squared. Keep that in mind. Yeah, then we have the similar relationship exists between intensity. Intensity is also directly proportional to the square of frequency, proportional to the square of what? The frequency. Please focus. Frequency, I can write that as IF squared. So I can put that in my red emphasis. Okay. Having established this thing, I will establish one more thing, then I will write a comprehensive formula for intensity. We have defined intensity from the perspective of energy and power and area. but based on its relationship with amplitude, frequency, and then density. Let me write for density. So intensity is directly proportional to the density. Directly proportional. Sometimes you might want to ask, why are we even defining how the relationship between these particular things, this intensity itself, and some other parameters? The reason for that is that if you know the relationship by your normal mathematics, if for instance a question says, oh, don't worry, when we get to questions, actively dealing with questions and calculations, you might see some of this. If a question says, oh, the amplitude of a particular string is doubled, what happens to the intensity? Then you will remember that, oh, intensity is directly proportional to amplitude square. So if they tell you that the amplitude is doubled, what do you think? Definitely the intensity will what? You have a quadruple. Yes, that's how to use it. So if something is doubled and you know that the relationship between that thing, let me use the green arrow. The relationship between that thing and intensity is a square relationship. Let me play a game. I'm going to hold on first. I'm going to hold on with respect to that. But just get me on that point. One of the reasons why we are emphasizing this relationship is so that you know how to approach questions where they talk about them. If a very straightforward question comes and says, oh, the amplitude of a particular string is doubled, what happens to its intensity? And they put option A, it is tripled. Option B, it doubles as well. Option C, it quadruples. As a good physics student who pays attention in class, you should know that the answer is quadruple. And just even because we have established that I is directly proportional to A squared, where A is the amplitude. And then the same thing applies when you're talking about frequency. Then I was talking about another thing. I was about to talk about density. Intensity is directly proportional to density. Density itself. So I'm going to write that as I, directly proportional to, this is the way we've been writing density all along. So keep that in mind. Now, if you put all of this relationship together, there is a general formula for intensity, which in this time around, generally, I can write I to be equal to, please, this one is of utmost importance. I mean, I can clearly, or it's not clearly, I can confidently tell you that if calculations will come out on intensity, this is one of the parts where you cannot, you cannot skip this one. So just keep it in your reservoir of formulas. So I'll go straight to define loudness. Now, because we up above in the note, because at the point I wrote loudness stroke intensity, you must have, you might have wanted to assume that they are the same, but let me just correct that. I'm going to put, let me change my ink back to black. I'm going to put intensity in its own class. So telling you that clearly, obviously, they are not the same. So, but let's talk about loudness right now. I hope you are taking notes and paying attention. Loudness. Loudness is a measure of the human perception of sound. Human perception of sound. I'm going to tell you a couple of things that it depends on. It depends on the intensity, actually, and the varying pressure of your eardrum, and also your sensitivity. That is sensitivity of whoever is listening or the observer. So let me just write that. It depends on I, intensity of sound. It depends on varying pressure of the eardrum that is listening. And this is similar to the second point, but we can also just add, it depends on the sensitivity of the ear of the observer. So just keep some of these things in mind. Loudness cannot be measured. So loudness cannot be measured because it increases with the intensity, but not directly proportional. So, and also it depends on the sensitivity of the ear, which varies from person to person. So some people, it's very loud. So some others, raise them. So increase it. I mean, for my listeners who are not, African inclined. In Africa, we say raise them for you to increase the loudness. But then, okay, let me just write it there. Loudness cannot be measured. Cannot be measured because it varies with the sensitivity of the listener. Sensitivity of the eardrums of listeners, which in turn varies from person to person, which in turn varies from person to person. So keep that in mind. We'll quickly move to the next thing. And this particular area we're moving to is of utmost, I've used utmost before. Let me use another thing. Of pertinent importance. I mean, waves, that's subheading. Waves formed in vibrating strings. Waves formed in vibrating strings. I'm going to make a couple of points under this, and they are all important. So actually, when you appear in my class, almost everything is important. So you have to pay rapt attention. When a string or spring or spring with one end fixed is vibrated from the other end, a progressive longitudinal wave is produced. So keep that in mind. When a string or spring, let me go to the next point. When a string or spring with both ends fixed is vibrated by plucking, tapping, or bowing. So let me just bring the idea of this plucking, tapping, or bowing. Now, plucking, you can see the spelling right there, Plucking, and then tapping, Tapping. Bowing has to do with something that you do with the violin. Bowing, Bowing. So keep that in mind. At a distance between the fixed ends, a stationary transverse wave is produced. So please, you see these points, they just look very trivial. But mind you, They are of capital importance. If you look at the first scenario, the result is different from that of the second scenario. The first scenario delivers a progressive longitudinal wave to you. The second scenario delivers a stationary transverse wave to you. Those things are far apart. So please, this is why you pay attention. Just and you go and read it and memorize it and have it in your reservoir as what you ask now for excelling in your physics exam. So you should know what results in a progressive longitudinal wave, and you know what results in a stationary transverse wave. So please keep those things in mind. The string can be made to vibrate in, let me adjust the position of that, in many different ways. Oh, this is one of the interesting parts of musical instruments. In many different ways. And there is always a fundamental frequency. We must have mentioned this in our first class of sound waves. On sound waves, I mean, what I mean by first class is if you have ever heard me teach about sound waves itself, you must have had the concept of fundamental frequency or just fundamental. Yeah. Yeah, we'll expand on it and then we'll build into harmonics and overtones. The string can be made to vibrate in different ways. E.g., the first position. The first position is the fundamental. And when you talk about first position being the fundamental, that first position can also relate to, there are other names that it has. Can also be called, it is called fundamental, first of all. Let me put that in red. It is also called, keep this in mind, also called first harmonic. Keep this in what? In mind. Or you can call it zero overtone. Very interesting stuff. Zero overtone. So sometimes in a question, they ask you, find, or it helps you to find, maybe they gave you the fourth harmonic. And they say, oh, from the fourth harmonic, find the zero overtone. You should know that they're asking you to, from the fourth harmonic, they're asking you to find the first overtone. Don't worry. The idea here is have this nomenclature in your memory. What I mean by nomenclature is like have these names, have this, this way of identifying stuff. Because the simple tweak, the simple difference between you understanding the question and not understanding it at times can be just how much of the different names do you know. So the fundamental frequency is also called the first harmonic and the zero overtone. So let me go to making you understand it better. The second position is now called the second second harmonic. Second harmonic. Or we can call this first overtone. You see that? Are you seeing a pattern? Second harmonic, first overtone. Then when we come to the third position, we can call that third harmonic, or we call that second overtone. So you must have discovered the pattern between harmonic and overtone is such that for n harmonic, we have a corresponding n-1 overtone. That's the straightforward relationship between them. So, and what most of this fundamental stuff and, second position and third position, how do they look like? At least, let's just talk about a string. Let's say the first position looks like this, just a single. Then the second position will look like this, some kind of double stuff. The third position will look like this. You see that? So that's how it works. Let me try and redraw so that it looks more appealing. Okay. Oh, that's not what I want. So that's how it looks. So this is like fundamental. Let me use the green. This guy is fundamental. This guy is the like second harmonic. This guy is like the third harmonic. And this fundamental is like the first harmonic already. Or we say 0 overtone. This one is first overtone. This one is second overtone. So just keep that in mind. It's very instrumental for, for later when we start calculating. So I was making points and I was at the third point when I mentioned this. So I'm going over to the fourth point now. The fourth point. And that is frequencies. Frequencies involve all multiples or harmonics. So the idea of this point is, let me just put that is, for your second frequency, that second position we're talking about, which is characterized by frequency. So that second position or second harmonic, all of that, you have to find the frequency of the second harmonic. How does it relate to the fundamental? It's equal to 2 of the fundamental, 2 times fundamental. So basically, the general formula is f of n is equal to n times f of 1. So whatever you are looking for, if I'm looking for the frequency of fifth harmonic, frequency of fifth harmonic, I just do f5 equal to 5 times f1. So whatever f1 is, I'll just multiply by 5 and get my answer. So that trend goes on. So let me just write a particular trend. If you have your f1, f2 is equal to 2 times f1, f3 is equal to what? 3 times f1, f4, you are following. f5, very good. So, and it goes on and on. The pattern continues like that. And the same thing applies to the wavelength. So when you have wavelength of the first one, or let's do it like this. Let's say you have, let me define the formula as it relates to wavelength for you. Lambda n is equal to 2L over n. So this is the guiding formula for the wavelength. Let me put some of these guiding formulas in red. Fn equal to n times f1. Why this one? Lambda n equal to 2L over n. So the meaning of that is that you have, for the first one, lambda 1, you simply have 2L over 1, and that gives you 2L. For lambda 2, you have 2L over 2, that gives you L. Lambda 3, you have 2L over 3. And then the pattern goes on and on and on. Let's go straight to some other things. Factors affecting frequency of strings. Frequency of strings. Let's just list them out. Take nothing for granted, because some of these things can surface in your multiple choice. Whenever you are tempted to play with very important classes like this, just know that some of the things that you will just gloss over and joke with can just be asked in your obligation, and that can be the difference between your A and your B. That will put you in a very tight spot. So please, just for the period of the class, pay rapt attention. Factors affecting frequency of string. The first one I will mention is the length. Length. And frequency is directly proportional to 1 over length. And the meaning of that is that it is inversely proportional to length. So once you are directly proportional to 1 over something, it means you are inversely proportional to whatever is in the denominator. So frequency is inversely proportional to length. What does that mean? As the frequency increases, the length decreases, or as the length increases, the frequency decreases. So they have an inverse relationship. Inverse relationship between what? Inverse relationship between frequency and what? Length. Keep that in mind. So how does frequency vary with tension? It depends on tension. Or we can say, or force. Force on a string. So how does it vary with that? The frequency varies directly as the square root of tension. So keep that in mind. Varies directly at the square root of what? Tension. And what does that give us? Definitely, as the tension is increasing, the frequency is increasing. Or as the frequency is increasing, the tension is increasing. So just keep that in mind. Let's go straight. We'll not waste time because we have a lot to cover. I mean, generally in life, you have a lot to study, and you need a lot of time to do that. So let's quickly get the most important points. So you go ahead and go and rehearse. Study across board. Density depends on density or thickness of the string. The frequency depends on density or thickness of the string, which you can describe sometimes as mass per length. Mass per length, per unit length. So that's the thickness. How does it relate to that? It is inversely proportional to square root, or it varies as 1 over that density. So inversely proportional to the square root, or varies like this. So they have an inverse relationship. If I will state it, in terms of relationship. So now if we are to combine all these 3 things I've mentioned above into one formula, you can have an important formula of frequency. Before I state that important formula, I'm going to write how it relates to about the 3 of them that I've mentioned now. So right here, we know that this is this guy over here is definitely length. This guy here, tension. And this guy, mass per unit length, or we call it the density. But this time around, that density is like, linear density. That's mass per unit length. So the idea here is take note of how they appear. So now if we are to say the frequency, let me now give you the frequency of the fundamental note. Frequency of the fundamental note. Which we generally know as our first position, right? Otherwise called first harmonic, or sometimes we call it 0 overtone. That particular frequency is given as, I'm going to write it this time around as F naught. F naught equal to 1 over 2L square root of T over. See, this formula, don't argue with it. Just store it in your brain, because it's very important. So take note of that. This formula is the frequency of the fundamental note. 1 over 2L square root of T over density. And what do all these things represent? I will repeat it again. Where F naught is frequency of fundamental note. Fundamental note. Your L is length of spring or string. Your T is the tension in the spring or string. This density is the linear density. And what do I mean by that? That's like mass per unit length. Mass per unit length. So when you see out utilizing these formulas, you discover that density, they might not give us directly in the question, but they will give us mass and length. What we will do? We will divide mass by length and get it, and then proceed. Do you get it? Yes. So another way of writing your fundamental frequency is that you can write it as, okay, let me quickly explain what I'm about to do now. In place of L here, L, in this formula above, in place of L, right here, I want to bring in the concept of, I defined wavelength as this. And you see L there. So I defined wavelength, lambda n, let me write that in black, lambda n as 2L over n. So, and now we already have above, in our formula for fundamental frequency, we have 1 over 2L, then square root of T over. Do you know what I want to do now? It's just the simple idea of this. Look at this. I want to say, if I'm looking for, see this F naught, or why do I put it as F naught? I think since I called it fundamental frequency, let me put it as F1. Yeah, sorry about that, but I have to make sure that I'm consistent with my naming. So fundamental, let me call it F1. So please correct that and call it F1. Okay, F1. Yeah, so F1. So F1, fundamental frequency. Now, in this particular formula, for lambda, this one, let me point at it. If I was to talk about the first frequency, this will be lambda 1 equal to 2L over 1, right? And that will give me what? 2L. So we know that lambda 1 equal to what? 2L. Are you seeing the picture? Yes. So if we are to rewrite F1, we can rewrite it as, you see this place where 2L is? I can put lambda 1 there. So F1 equal to 1 over lambda 1 square root of T over. This is another way of getting your fundamental frequency. So do you know why getting the fundamental frequency is important? Because once you get it, you can get any other thing from it. So if you know how to get it, you are good to go. So please take note of these formulas as we proceed. See, that is why you have your home and you have somewhere to go after school. You go and study these things. So as we are moving through them, you might not be digesting them in full. You say, oh, I get that. I see what's happening there. I see what's happening there. So your duty in class is to see what's happening there. Your duty at home or in your closet is to digest it by reviewing it and say, okay, I get it now. That's it. So let's move forward. If you might have seen when you started your calculation on waves, or at some point in wave, you must have seen something like V equal to F lambda. That is a very common definition of speed as it relates to frequency, and wavelength. So if we are to introduce this kind of thing in our formula, and we say, okay, let's find the velocity of the fundamental frequency. If we are to find the velocity of the fundamental frequency, let me call that V1. It will be equal to F1 times what? Lambda 1, Abi? Oh, I didn't want to use that, Abi. Abi, for my non-African listeners, perhaps I have any. Abi means, are you following? It's as simple as that. So V1 equal to F1 times lambda 1. So get that idea. Let's proceed. V1. How do I factor this into this now? I just move this definition, this particular definition of F1, I move it into here. So let me write V1 now. V1, which is my velocity for the fundamental frequency, I can write that as 1 over lambda 1 square root of T over density times lambda 1. So the idea here is that this will cancel out this, which I have always advised as I teach. Don't cancel out things. Just let it be. So remove that cancellation. Don't cancel out. Stop it. Don't start canceling out things. It's not a good way of expressing your algebra. You know what's happening. So in your mind, let this one cancel out this one. But you don't have to put the stroke in reality. There are some penalties. Some people penalize you for canceling out things. I mean, literally. So please, just humbly take my advice. Don't cancel out things on this. So you can cancel it in your mind, then proceed with the next line of equation. So let's see. So if I cancel that in my mind, I know that I will have my resultant equation to be of this form. So this is a way of telling you that the velocity of the fundamental frequency is defined by this. So just keep all of this in mind. There will be very interesting stuff to play around. Can you see that formulas are showing up now? And you need to, turn on the memory lane of your brain. Yes, because it will be very important here. And this is where you demand maximum focus. Your memory needs to be available for these things. So you must be dedicated to it. Let's go to the next subheading. Wave. Oh, let me switch back to my wave formed in air columns. You must have discovered that the discussions we just had are for the waves that are formed in strings. So we are moving to a different instrument now. So discussion, we just have a look at it. Frequency, okay. Let me calm down. Yeah. Waves formed in vibrating string, yeah. So that was like what led us into fundamental frequency and all of that. So we're moving to another one, wave formed in air columns. So let me start again by making some very important points, which cannot be overemphasized. Number one, a stationary longitudinal wave is produced when air column is vibrated. So imagine a multiple choice, or what we commonly call OBJ, objective question, asking you that what kind of wave is produced when an air column is vibrated? And they put in the option A, progressive transverse wave. Option B, progressive longitudinal wave. Option C, progressive mechanical wave. Option D, stationary longitudinal wave. What's your answer? Stationary longitudinal wave. Now, just imagine that you say it's not important, it's not important. You will not know the answer to that question. And unfortunately, just by not paying attention in class and then not reading on your own and taking note of this important point, you will miss point here, point there, point here, points there. And that's how people miss a lot. And they're not able to measure up to what is required. So that's why I say, as you are in class and when you are studying, pay attention. Don't trivialize those things. So let's proceed. A stationary longitudinal wave is produced when air column is vibrated. That is, let me paint a scenario. That is, when you place a tuning fork near the mouth of a tube or a pipe containing air, that tuning fork, in many other terminologies, they call it a vibrating source, a vibrator. If you place a vibrator at the mouth of a pipe containing air, you tend to produce longitudinal waves. So get that picture. So a tuning fork placed near a tube or pipe is an example. So the next point I will make quickly is that the vibration has can be of three kinds. So vibration in air column, let me write it. Vibration in air columns can be of three kinds. Number one, free vibration. And this occurs if the air column is set into vibration by a point source of energy and left to vibrate by itself at natural frequency. So if the column is set into vibration by a point source of energy, which could be our tuning fork or vibrator, and left to vibrate by itself. Wait a minute, please. And left to vibrate by itself, at natural frequency by gradually moving the source away. So it's more like all of these things, they are just, English. You are just painting your idea in written words. What happens in free vibration? I come near a pipe, I put something that can, be a source of vibration at one end, and then I remove it. Then I now allow that pipe to keep vibrating until it naturally stops. So that's a free vibration. Let's move to the next one. Is the other type of vibration that we can have here is the forced vibration. And here the idea is that give me a minute. The idea is that you can set something into vibration. An air column, since it's air column we are talking about, an air column is set into vibration by an extended. So in the case of free vibration, we said it's a point source, but here it's an extended source. That is, let's say the thing was already in vibration before, and then we put another one. You understand? So instead of it to naturally stop, it will now start another one again. So there is an extended source extended source of energy. And then one of the ways to really emphasize it being forced is that instead of just putting it there and removing it, we keep it there. So an air column is set to vibration by an extended source of energy and kept in contact. So you are experiencing a continuous kind of vibration. Excuse me. So in this case, we tend to hear louder sound. So the frequency we have in this case is also called the frequency of forced vibration. So just keep that in mind. But this is the point. Let's now go to the other kind of vibration in air column, which is called resonance. Resonance. Resonance is a special case. A special case of forced vibration. Where the frequency of the forced vibration is the same as the natural frequency. Of the body set into vibration. So the big idea here is that we have maximum amplitude and loudness. But just keep this definition in mind. Go home, digest it. So we have two things that are interlocking. The frequency of forced vibration being equal to the natural frequency. Keep that in mind. That's what creates resonance. And let me quickly add the point that at resonance, there is maximum amplitude and loudness. Keep that point in mind. So that point, we made it under the second point. And we said vibration in air column are of three kinds. Now let's go to the third point, because we are making points. As for the wave in air column, the waves in air column. So the third point is that the air columns can be enclosed or open pipes or tubes. Excuse me. So most of the time, what we call closed pipes, we are referring to pipes open at one end and closed at the other. So we are looking at something like this. So there is open end, and this is the closed end. So generally, we call this kind of air columns closed pipes. So don't get confused. So far, there is one opening, and then it's closed somewhere else. And also, whenever the scenario is going to vary, that is, if it is closed at both ends, something like this. So a pipe closed at both ends leads you into a string. So the question will specify that it is closed at both ends. So, but whenever the question just mentioned closed pipe, it is this scenario that it is painting. If it wants you to use closed at both ends, it will state it categorically. But when we are talking about open pipes, we are referring to a case. So this is just like me saying, this is what we are referring to. This is not part of the pipe diagram. There's no pipe that has this thing, please. So this is like me saying, okay, see what we are talking about. So for open pipe, we are talking about a case that looks like this. What do we observe? So you notice that open and open. Are you getting me now? Or let's say, we can also have it this way. Open, open. So let me move one away. So these are the cases that we can have. So you see me pointing at the open ends. So let's not waste time. Let's quickly move forward. So for the closed pipes, let me quickly note. For the closed pipe scenario, they have, that is this guy is over here. They have odd multiples where you want to find their frequency. Their frequencies are odd multiples of the fundamental frequency. That is, take for instance, if you ask me for a closed pipe, normally the fundamental frequency, you will get to understand why this is an important point now as I explain. The fundamental frequency, if we know that as a F1, the idea for closed pipe, and please, this is as important as you going to digest it and memorize it. For closed pipe, when you have fundamental frequency like that, and I'm asking for the second harmonic frequency, second harmonic, which is also first overtone. The idea is instead of 2F1, for closed pipe, it is 3F1. Are you seeing that? That is why it is an important point. Let me shift this thing back so that it doesn't enter that place. Oh, excuse me. Excuse me. Let me try that again. One last try. If it doesn't work, we'll move on. Okay. So let me move it here. Yeah. So 3F1. That's what we meant by odd multiples. So instead of 2F1 for the second harmonic, we have 3F1. So guess what the third harmonic will be? Mind you, we only work with what? Or second overtone. Mind you, we only work with odd multiples in this case. So if we have had fundamental to be F1, second harmonic to be 3F1, guess. Guess what the third harmonic will be? We only work with odd multiples. What's the next odd number? 5. You are right. 5F1. That's it. And it goes on and on like that, such that the fourth harmonic or the third overtone. You see why teaching and learning is important. Even if this is your first encounter with this concept, you are learning. And so you will just take note of it. 7F1, that is the next. You understand? So we are unraveling how it works. to you so that when you encounter it elsewhere, you would have been knowledgeable. And then we can, by the time we are rehearsing formulas, you are well loaded to approach them. So this class will soon be over, but let's consider a few more things. Like the open pipes. Let's talk about the open pipes now. What happens there? Open pipes. And by now you should get the idea when I say open pipes. Definitely open at both ends. So that's what we consider as open pipes. So open at both ends. So I've told you whenever a pipe is closed at both ends, it forms a string. And the question will categorically state that it is closed at both ends. So I've said these things. This is why we teach, so that you don't miss the in-betweens. With both ends open. Open pipes are the ones open with both ends. So the main gist here is that in open pipes, we have, oh, let me switch to my black pen. We have all multiples of the frequency are similar to that of a string. That is, they are normal. You know, when we're talking about string, you must have discovered that was where we first of all mentioned, the second harmonic equal to 2F1. So yeah. So this same principle applies when you are talking about open pipes. So the idea is that we are saying, oh, if the fundamental frequency, in this case for open pipes, so the fundamental frequency has been defined to be F1. For open pipes, the second harmonic or the first overtone, and most of the time, this is what we call our F2. So that's F2 will be 2F1. That's like the normal thing that happens. So you can see that the abnormal guy is these closed pipes. So the open pipes, which is open at both ends, follows back to the normal order. The third harmonic, which is the second overtone, goes with 3F1. So, and it goes on and on and on like that. And so there was a point I failed to mention in closed pipes. In closed pipes, their wavelength, this is the formula for their wavelength, 4L/N. Take note of that. So if, for instance, we are looking for the wavelength of the fifth harmonic, it is going to be lambda 5 equal to 4L/5. So you just, by that time, they would have given you what your L value is. You plug it in and you get your answer. So that's how it works. So keep that in mind. So as for the open pipes, the formula for wavelength is lambda n equal to 2L/n. Take note of that. These are things to take note of. Let's go to the other point. And by the time I finish making the point, I will wrap up the class. And then we'll continue in subsequent classes. So the fourth point is that the strength of resonance in pipes, whether they be closed or open, the strength of resonance in pipes decreases with length. So decreases with length. The meaning of that is that we can say it is inversely proportional to length. So strength inversely proportional to length. So the idea is that this concept is trying to tell you that the second position or the second harmonic will always be weaker than the first. Then the third will be weaker than the second. You get the idea? So when you have F2, or let's say the second harmonic or the second note is always weaker than the first. The third note is always weaker than the first, always weaker than the second. So the thing is that as you increase, as you increase the position from first position to second position, the strength of the resonance decreases. So just get that point straight ahead. The next point, length. The length of air can vary in a pipe by introducing water. And then raising or lowering the water level. This is more like a very, very straightforward concept. Now, if I have a pipe and I put water, if I put water to half of that pipe, it means the remaining part of that pipe that is not occupied is occupied by air. If I put water to 3/4, it means the remaining 1/4 is occupied by air. If I put water to 1/5 of the pipe, it means the remaining 4/5 is occupied by air. That is the point that that's the point being made. It's just English. So the sixth point, which is like our penultimate, second to the last point, velocity. Velocity of sound can be determined by resonance tube experiment. Velocity of sound can be determined by resonance tube experiment. I'm just going to write the formula straight up. And then we'll actually use it when we are dealing with actual questions. So let's do this. V equal to 2F L2 minus L1. Just take note of that. Just take note of that. And this case is when you are using different resonating length. I would love to keep things straightforward for now until we start dealing with actual problems. Then you will see some dynamics. That's why you should pay attention. So keep this one formula in your reservoir for now. Then there's another case that has to do with when we have different frequency. This first case was when you are dealing with different length. Different length. But in the case where we have different frequency, this is let me pause and think about that first. Okay. Okay. I'm not going to give you that for now. I'm not going to give you that for now. Let's just keep it at different lengths for now. If I will give you for different frequency to come later in the future, or while we are solving problems. So let's see. Just keep this in your arsenal of formulas for now. Let's go over to the next point. 7. For strings and pipes. Oh, this 7th point, we have already established it as we're explaining. Closed pipes, open pipes, and all of that stuff. So by now you should know that for a pipe closed at both ends. Okay, that's just the 7th point. Let me establish it. For a pipe closed at both ends. That's like a string. That's clearly a string. So we know that F1, F2 equal to 2F1 in those cases. And then we know that lambda, so, or you can say the generalized formula here is Fn equal to NF1. We know that lambda 2 or lambda n, let's write that lambda n equal to 2L. Let me put it this way. Give me a minute. 2L over n. We established that. Ready? And then let me see. We established, okay, this one is 2L over n right there. Yeah, so this is like a string case. Yeah, open at both ends, close at both ends. Yeah, 2L over n. Just keep that in mind. Then what else are we looking at? What else are we looking at? Okay. And then generally, since we have established, this one is important. We've established some of the following points. Generally, we know that F is directly proportional to 1 over L. So the meaning of that is in your mathematics. So please, let me just put this formula. And this was talking about pipe closed at both ends. So keep that one in mind. But I'm not talking about a general description now. And where does this general description I'm about to talk about now apply? When you are asked in OBJ and said, oh, the frequency of a pipe is given to be 3 hertz. If the length is doubled, let me quickly write that question. It's not an imaginary question. I'm literally telling you how the questions can come. The frequency of a pipe is 3 hertz. What happens to the frequency if the length is halved? Very, 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 very important question. Now, A, we say frequency doubles. Let's see, that's our answer. B, we say frequency divides by 4. Or let's say, when you say divides by 4, it's like frequency decreases by a factor of 4. Please, also practice your English language. Frequency decreases by a factor of 4. C, frequency is halved. D, frequency increases by a factor of 4. Now, what do I want to utilize? The idea, we have established this before, but I want to use it in solving problems. And this is where we end today's class. We know originally, let's call this the solution. We know originally that frequency is inversely proportional to length. And so we can establish a relationship. If we, in maths, you must have discovered that when we want to write this now as equal to, we put a constant of proportionality, say K over L. And we can get the relationship to be FL. So when I say F1, L1 equal to F2, L2. This is how it works in maths. So whenever we are given a first frequency, the first frequency we are given in this case is 3. 3 times L1 equal to, we are looking for what happens, F2, L2. But we are told something about the length. We are told that the length is halved. That is, L2 is equal to L1 over 2. That's the meaning of halved. L1 is the initial length. We are now told that the length is halved. So that means L2 is definitely L1 over 2. So let's put that into our formula above. 3L1 equal to F2 L1 over 2. Are you seeing that? So by the time you go further, you see 3L1 equal to F2 L1 over 2. Now, like as I've always said before, I can divide both sides by L1. Normally, somebody who is just, solving it roughly or anyhow, as I've said, don't cancel out things. We just say, this cancel this. But which is not good for exam conditions. I'm telling you, just say divide both sides by L1. So I have 3L1 over L1 equal to F2 L1 over 2 L1. So instead of doing cancel here, cancel here, no, cancel it in your mind. Cancel it in your mind, or cancel it in your rough sheet. And then we now have 3 equal to F2 over 2. When we cross multiply, we can now say F2 will now be equal to 3 times 2. F2 is equal to what? 6 hertz. And now that we have gotten 6 hertz, F1 was what? 3 hertz. And F2 now is 6 hertz. So our correct answer has to be what? The frequency doubles. So please go home, study all that we have done today, and we will meet in our next class.